Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we will discuss a little bit new topic with respect to even the topic we discussed in the last lecture. In the last lecture, we discussed different type of constraint motions, and there we somehow classified different type of constraints, and we said that constraints are mainly the conditions or limitations on the kinematics of the particle. So, for example, if the particle is always moving in a well defined trajectory, if the particle is always in contact with a surface, if the particle is always within a domain, if the particle is always outside a domain, this type of things. So, then we have said that there are several type of constraints depending on their nature. The first one we said that whether it depending on whether the time is explicitly appearing. So, constraints said that depending on the fact whether time is explicitly appearing or not, the constant can be rheonomic, where time explicitly appears, or scleronomic, where time does not appear, okay, explicitly of course. Then if it is just equality, then we said this is bilateral. Then if it includes inequality, then we said this is unilateral. Then we defined two very important class of constraints. The first one is holonomic constraint, the second one is non-holonomic constraint. Okay. So, the holonomic constraint should be always put in a form f x, y, z. So, for 3D of course, for 3D space, okay, and t will be equal to 0. That means, it should be an algebraic or a trigonometric or exponential, but it is an integrable equation, okay, involving the position coordinates and at max the time explicitly can also come into the expression of a holonomic constraint. Okay. So, for non-holonomic constraint you cannot write like this. So, you cannot put in this form. Okay. So, I say this is not possible. Okay. So, I also said that there are few cases where you can have holonomic constraints, okay, which are not a priori holonomic. For example, I gave you an example of this. So, z dot is equal to some constant time x dot. So, you can say okay, here the not the position coordinates or time, but their dots, that means the velocity coordinates, okay, they are related by a constant, but you know that if you integrate them, you will actually have z is equal to alpha x plus c, which is an algebraic equation again relating z and x, and that is why this is again a holonomic constant. On the other hand, I said if I say that x dot is equal to some alpha x y, then you cannot actually integrate very simply, and that is why this is a non-holonomic constant. And also all these unilateral constants are by definition or by construction are non-holonomic constraints. Okay. In this lecture, what we will discuss is the dynamics imposed by such holonomic constraints. So, whenever in nature we see the holonomic constraints, they are of advantage because we can finally write some equations in form equation for the corresponding constraint, and we can do some analysis. Okay. And if you see that, if you think a little bit that for a holonomic constraint, if you always have an equation involving 2 and more coordinates, then actually by the introduction of holonomic constraints, you are effectively reducing the effective number of coordinates or position coordinates for the associated motion. Okay. So, if this is the case, then holonomic constraints are also important to reduce the number of effective independent coordinates, position coordinates for the corresponding motions. Okay. Now, finally, I want to make one point that whenever for example, let us say I have a holonomic constraint which has a form like this. Let us say z is equal to some a cos omega t, where a and omega they are constants. Okay. So, this is, I mean, of course, from the definition we can understand that this is a constraint where you have if z minus where you have z minus a cos omega t is equal to 0, and that means you can actually write f of z and t is equal to 0, and that is a holonomic constraint. So, your question can be that how can that reduce the effective number of independent coordinates. So, here the point that if you know a position coordinate in terms of time explicitly as a function of time, then you see that just by knowing the time instant you can actually say, and if you know the law how it changes, how the position coordinate changes as a function of time, then you can actually tell me, for example, in this case if I tell you t, since a and omega they are constant for one motion, you can calculate me z immediately. So, z is again not an independent coordinate. Okay. So, in that way this is also reducing the position variable by 1. Okay. So, actually there is a very useful thumb rule is that every single holonomic constraint is able to reduce the number of coordinates, position coordinates, or the degrees of freedom of a motion, okay, by 1. Now, the point is, in nature whenever we have holonomic constraints, we see that most often there are forces which are associated to those holonomic constraints, they have some interesting similarities. What are the similarities? I am coming to that. Most of the cases you will see, so if I just tell you one by one, take the case of a simple pendulum, okay, of a fixed length L. Now, so there is a pendulum and this L is not changing with time. Okay. Then how would you actually solve the dynamics of this bob? You say, okay, there is g which is acting downwards due to the gravitational acceleration of earth, and then you say that since this string is actually of fixed length, there is a tension which is working along this string, okay, but inward direction. In an arbitrary position like this, g is always vertically downward, but this tension is now along the string, okay, and it is radially inward, you can see. Okay. Then we can do the component analysis and we talk about the dynamics, okay, the force balance in different directions. So, for example, here you will have a force balance in this radial, the outward and inward directions, and also the tangential directions with respect to the arc of the circle, okay, that you all know. Now, the point is that if you think what is the origin of this force, the origin of this force is the elastic property of the string or the wire, okay. That is the property which maintains the length of the wire. So, if you want to deform by adding this mass to the string actually protests any change of the length. So, we will actually see that whenever there is a holonomic constraint, the force associated to maintain that constraint is coming from some type of elastic nature or some how to say, like some stiffness type of property. So, for example, already you have seen for spring there is a stiffness property. Whenever you want to deform the spring, it actually tries to give you a force in order to restore its original length. Okay. I am just going to another example. So, which is the example of a particle moving along an inclined plane having an angle theta with the horizontal. Okay. Now, if here in this case I say that the holonomic constraint is that the particle is always in contact with the inclined plane, then again you see that what is the force associated with this constraint? That is the reaction force given by this surface to this particle. Okay. So, the particle is, of course, you know that the weight is always acting vertically downward direction, but when the particle is here, the surface, okay, since the particle is here, the surface actually gives a normal reaction to this particle, and that is also comes from some elastic property or some reaction mechanism. So, for example, if the particle is giving some force to this one, as a response it will give some reaction to that particle. Okay. So, whenever you have this, then you can say that this type of forces, so here this reaction force which is normal to the surface, okay, and of course here the tension force which is radially inward, okay, the forces associated with the constraints, and that is why they are called force or forces of constraints, or simply constraint forces, constraint forces. Okay. You can call them FC. Okay. Now, you see another similarity is that, so the first similarity I think you have all understood, it comes from some response. Okay. Whenever there is a particle which touches this body, this one responds to the particle. Here also whenever the mass is attached to the string responds to that particle. Okay. So, forces of constraints are somehow the response of the entity other than the particle, okay, to which the particle is constrained to move or to which the constraint is associated with. Okay. Another similarity here you see that the force of constraint is always perpendicular to the motion of this particle. So, if you just think of an infinitesimal displacement of the pendulum, you all know that will be along the tangent of this arc of the circle. And what is the direction of the tension? This is along the radial direction, of course inward, and so they are perpendicular. Okay. Here you see also eventually the direction of the motion of the particle is actually in this direction along the inclined plane, and the reaction force is perpendicular to the inclined plane, and that is why this is also perpendicular. What is the meaning of that? In these two cases, if they are perpendicular to the infinitesimal displacements of the particle, then what will be the work done by those forces? The infinitesimal work done will also be 0, because F dot dr. So, I am just writing, so F c dot dr in both these cases, this one and this one, is equal to 0, and that is nothing but dw. Okay. So, this is 0. So, that means that there is no work done due to these constraint forces. Now, up to this was correct, there is no problem. But the problem comes, let us say if I say that I have a holonomic constraint where time explicitly appears. So, it is a holonomic and rheonomic constraint. So, for example, this pendulum will now be a pendulum, but with flexible length, and then of course, the length I can just keep this law if you want, 1 plus sin omega t. Okay. The length is actually, so here it would be like this, and then L, and then it would be a little bit bit longer, then it will be a little bit longer. Okay, you just neglect those curves, they are always straight lines. Okay, yeah. So you see they are like this, and there is no arc of circle which is maintained here. Okay, and that is why you see that although in this position that tension was radially inward, here the tension is also radially inward, here the tension is also radially inward. If you think that this particle is moving in the arc of a circle, then only this infinitesimal displacement would be perpendicular to this direction of the tension force, otherwise not. But what happens here, the infinitesimal displacement is not exactly perpendicular, because in course of time its length is actually changing. Okay, and this length is changing by dl amount, which is given by L0 d of 1 plus sin omega t. Okay, and one can actually show that this dl is no longer perpendicular to the radially inward direction, whereas the tension is always acting along radially inward direction. We can do another example where you can see this thing, that I have some arbitrary position L, okay, and from that I could move like this. So, when it is coming back to the mean position of rest, it is actually going away, and then if the length were constant, then you see that I am just taking this one actually to be very close. So, theta is actually very small, tends to 0. So, this is an exaggerated figure, try to understand the meaning of this figure. So, whenever I have this, then I can again say the tension is always along the string. So, it is like this, it is here like this, the G is like this, G is like this, and then finally what I am saying, that this is the direction tangential to the arc of the circle if the length were fixed, but now the length is changed, and actually according to this law the length would be here. So, the particle is actually should go like this, and whereas the particle should go like this, then of course you understand that this displacement direction is no longer 90 degree or perpendicular to the direction of the tension. Okay. And that is why your force of constraint is no longer perpendicular to the direction of the displacements in both these cases, where the length of the string is changing explicitly with time. Then one possibility to handle this situation is the following: if we think that we do not travel in time, that means we do not let the system evolve according to its real evolution. That means that if, let us say, I am just doing some thought experiment. So, for example, I can think that let us say I have a system of simple pendulum, okay, with some variable length, I mean with a string of variable length L, which is L0 times 1 plus sin omega t, and I somehow maintain an initial distance here, which is, let us say, my L0 for example. Okay. So, I am saying that this is my t is equal to 0, okay. And I know that now if I just let the system evolve, then with t not equal to 0, when t increases from 0, this length would increase, and actually instead of coming here, it would come here for example. Okay. So, that L will be L0. Okay. This is the inverse case. So, I have started now the motion from here, but if what happens if instead of just releasing this bob from this point, I just think that at this t is equal to 0 if my bob was not here but here, for example. So that means I am just thinking, so this is not a real evolution, I am just thinking that if at time t is equal to 0 I start from a different position. So that means that at the same time point, one is a real system, another one you are imagining. Okay. So then you can actually say, okay, then what happens, since the t is equal to 0, the initial length should be L0, but now according to your imagination, your L0 will be the length at this position. Okay. So instead of comparing two instants, instead of comparing the position of the bob as two instants, let us say t is equal to 0 and t is equal to, let us say, some 2 seconds or 1 second or 5 seconds, I will do the following trick. I imagine an equivalent imaginary system in which I just change the initial condition. And then I say, since the initial length is always L0, because that is the constraint is all about. Okay. And then I can say that if I compare the positions here and here, they will be on the arc of a circle. And in both cases, the tension forces will be always acting along the radial direction along the string. Okay. So you see that you are not comparing two positions. Okay. You are comparing one position which you have prepared and another one which you are imagining to prepare. Okay. Now if you comparing these two, then there is of course now there is a displacement between this real position and the imaginary position. And this displacement is not a displacement which you can see in nature, okay, because you have not actually released the ball at all. This displacement is in your brain, this is in your imagination, this is virtual, this does not exist in real world, and that is why this displacement is known as virtual displacement. You can do the same type of virtual displacement, okay, and that is why this type of displacement is known as virtual displacement. Okay. So virtual displacement means that the displacement between a real position and an imaginary position at t given. That means here we have just chosen for t is equal to 0. I can do the same type of trick for any other arbitrary t. Now you see, at t is equal to, let us say, 0.5, this L will have a value which is 0.5. Now if I say that I start my motion, okay, which is t is equal to 0 from this point, then after 0.5 seconds the particle should go like this. Okay. I can say, if instead of that I start the motion of the bob from this position, then after 0.5 second it can go here, for example. Okay. Then again I can compare the position of this two particles here, and that will be the virtual displacement at t is equal to 0.5 second. Okay. So you understand what I am trying to say, that virtual displacement you cannot realize or you cannot make in a real system's evolution. Virtual displacement means that you just have all the positions possible for a system which is evolving, and now you take one time instant. You imagine another possible position, okay, for that particle at that instant of time just by imagining. Okay. Then the discrepancy between these two will be giving you, I mean in position, will be giving you the virtual distance between these two positions, and the position vector related to that will be called the virtual displacement. Now, the last point, which is very important, is that can I imagine any displacement? No. The virtual displacement is a displacement which is virtual, but it should always be consistent with the constraint. That means, I can take at t is equal to 0 another point on the circle of radius L0, but I cannot take any other point at t is equal to 0 on the arc of any other circle which has a value L0 by 2, for example. That is not possible. So, for example, you cannot say okay, at t is equal to 0 I imagine a point which is here, okay, because that is not possible. That is not consistent with your constraint. Okay. So, virtual displacement is an imaginary displacement okay, without changing time, okay, is an imaginary displacement consistent with the constraint, with the given constraint for a motion. Okay. Okay. Now, what is the advantage of virtual displacement? That if you, instead of taking real displacement, if you take virtual displacements, then even when you have explicitly time dependent constraints, that means rheonomic plus holonomic constraints, okay, then you always have the work done associated with the virtual displacement to be always 0, because virtually always you are just, since you are freezing the time, you are just always thinking of the same length, because L will be same for a given instant of time, for a given value of time. Okay. And then if you are now thinking an imaginary position and your real position is given by some L, okay, those two will or must situate on the arc of a circle of radius L, okay, radius L at time t, and that is why the direction of the virtual displacement will be tangential to that arc of the circle, and the tension which is acting along the string and but radially inward will be perpendicular to that. And that is why if we consider virtual displacement then the constraint forces Fc, okay. Of course, we understand here constraint forces means mostly associated with holonomic constraints, This will be perpendicular to the virtual displacement, and hence Fc dot delta r will be 0. So, if we consider virtual displacement, then the constraint forces will be perpendicular to there, okay, both for, that is important, both for cleronomic and rheonomic holonomic constraints. Okay. So, this is a very general principle. So, of course, this is a work done associated with the virtual displacement, we call that virtual work. Okay. So, I can now write a principle by which saying that the constraint forces Fc do not do any virtual work. Okay. So, if we can write that, then this is the principle of virtual work. This is known as the principle of virtual work. Virtual work. Okay. Then what is the advantage from this? Then we can write that, okay, so for a system, okay, for a system, if the total force, instead of system I can write for a particle, yeah. If the total force acting on the particle is equal to F, I can actually decompose that in two parts, F I, okay, plus F C. F I is the force which is trying to cause any acceleration or something, just so this is a force due to some external entity, okay, and this is the force due to some constraint. So, for example, for a pendulum, once again the force F I is nothing but the weight of this mass, okay, because this particle is moving in a gravitational field of earth, okay, that is why the G is acting on this and m times G will be the weight force, and that is F I, whereas the tension force is only coming because of the fact that the particle has to be attached to a string which maintain its length L, okay, and that is why T is coming. So, this tension force is, for example, a constant force, okay. So, if for a particle you can somehow distinguish this F I and F C, then you can have some simplification, we will see in 1 minute. Before that, I am also trying to say that what are F I and F C for this particle moving in an inclined plane. So, again F I is the force due to the weight, okay. So, that will be mg, okay, moving downwards or acting downwards, and R will be the force of constraint, and that is present only because we have constrained the particle to move always being at contact of the inclined plane, okay. If I write this, then Newton's second law says okay, m r double dot will be equal to F I plus F C, okay, and then I can do actually a contraction with virtual displacements in both sides, F I plus F C dot delta R. Now, you know that F C dot delta R is always 0, that is the principle of virtual work, and that is why finally you will have m r double dot minus F I dot delta R is equal to 0, okay. So, this is known as the DAlembert's principle. DAlembert's principle. So, DAlembert's principle actually say that in the formulation of dynamics, if you introduce delta R instead of dr, the real displacement, okay, if you introduce instead of the real displacement the virtual displacement, then in the whole dynamics you do not have to account for the forces of constraints. And that is quite advantageous because of the reason that most of the cases, although we know that there is a tension force, you do not know the exact law for the tension force. For example, for gravitational force, for Coulomb interactions, we know the law is of central force, say inverse square law. For magnetic force, you know this is V cross B, but tension force we do not know. It may or may not have a central nature like that. Okay. The same thing for the reaction force. We know there is a reaction force, we use that sometimes, and finally, if you see that most of the time we either for knowing some for to solve the system we eliminate those constraint forces by smartly using the force balance in different directions, or we actually determine them. Okay. But the point is that can we, for our usual classical mechanical systems, natural systems where we are dealing with simple holonomic constraints, can we somehow get rid of totally this get rid of entirely this forces of constraints? Okay. The answer is yes, if you use this virtual displacement. Okay. Now, just before wrapping this lecture up, what I will simply do is just giving you a small example or small application of DAlembert's principle, that is, so using DAlembert's principle, how to find the equation of a simple pendulum. Okay. So, first we have to understand that the first challenge is we do not write anything about the tension force. Okay. We forget that, and still can we find the equation of dynamics. Okay. So, for that we will just use the constraint. What is the constraint? So, let us say the pendulum is moving in xz plane and the length is fixed at L, okay. And now, so L square is equal to x square plus z square, given this is x direction and this is z direction, okay. This is my convention. So, I can actually say this is the constraint which I will use, and from this constraint what I can easily have that x delta x plus z delta z is equal to 0. Now, you see that this is the infinitesimal form of the constraint, okay, associated with the infinitesimal virtual displacements. Okay. And this makes by definition this to be a proper virtual displacement. So, virtual displacement infinitesimal, of course. Okay. Because if the virtual displacement is not consistent with the constraint, then this is not by definition a proper virtual displacement. Okay. So, if I do this, then the corresponding differential form associated with the virtual displacements will be simply this. And then DAlembert's principle simply says that DAlembert's principle gives, so you just have a look. So, this is DAlembert's principle, m r double dot minus f I. So, here what is f I? F I is simply the weight force. Okay. So, you just write, and that is along z direction, but downwards. Okay. So, along minus z direction actually g. Okay. So, g is in this direction. Okay. So, what I can say, I can actually do the component analysis along x direction and z direction. Okay. So, DAlembert's principle simply says that m r double dot minus f I dot delta r is equal to 0. It does not say that this is 0. Remember, this is a caution, point of caution. This is simply perpendicular to delta r, that will be 0. Okay. So, you should not forget this part. Okay. And then you say, okay, then m x double dot minus, so along x direction there is nothing. So, I can simply say that I can write that m x minus, somehow I just write the f in the x direction, okay, times delta x. I am doing the dot product of course, plus m z double dot minus f z, okay, and delta z will be equal to 0. Okay. This is my DAlembert's principle. Okay. So, this part is actually 0, this is 0. If you exclude the force of constraints, then there is no force along x direction. Okay. And along z direction you just have this g. Okay. But according to our convention, this is minus mg. So, this should be minus mg. So, the equation should be m x double dot delta x plus m z double dot minus minus plus g delta z equal to 0. Okay. So, you will have then two equations, one is this one, the another one is this one. Okay. You can just put this thing over here. So, you can simply say, okay, I can have then from this delta x will be equal to minus z double dot plus g times delta z by x double dot. Okay. And then again from this equation I have delta x is equal to minus z delta z by x. I can equate this two. For having something very interesting, if you equate them, you will have z double dot plus g by x double dot will be exactly equal to z by x. Okay. And then I can simply write the equation over here, okay, z x double dot minus z double dot plus g x equal to 0. Okay. I can now do a trick. So, in order to have the final equation of the simple pendulum in terms of our popular form, okay, we have to write this in polar coordinates, that is r and theta or L and theta. So, of course, you know that we now use x is equal to L cos theta. I mean, so if theta is this angle, then z will be L cos theta and z will be L cos theta and this will be L sin theta. Okay, yes, this will be L sin theta. Okay. L sin theta and z will be L cos theta. Okay. For theta tends to 0, x will be L theta because sin theta tends to theta and cos theta tends to 1. So, z will be simply tending to L, which is a constant. So, then what happens if you use this one, you will have z is L, x double dot will be then L times theta double dot. So, L times theta double dot L times theta double dot minus z will be a constant almost. So, z double dot we can neglect and there is a minus g times x, x is again L theta. Okay. So, I can write this equal to L theta times g. Now, one L will go away, you will have theta double dot will be equal to g by L theta. Now, you can see this is the famous and popular form of simple pendulum for very small theta angle. Okay. Aren't you happy with this formulation? Of course, you must be, because you see that even without using at all the tension force, you have simply found the solution for simple pendulum. Okay. Now, remember that this DAlembert's principle we have formulated in such a way that the virtual displacements and the virtual works are associated, and that was actually done in order to include all the constraints which are holonomic and rheonomic, that means explicitly time dependent. My question to you, can you also find the equation for a simple harmonic oscillator, but with variable length, and the length L is actually varying just like this. Okay. Of course, you know that you can simply use DAlembert's principle here in this case, and you can find the equation of dynamics without even introducing the forces of constant, that is the tension force. Okay. Can you also use DAlembert's principle in order to find the motion of a particle along the inclined plane? Okay. Think, and I think you will be successfully doing that. Thank you very much.